Yep. Yep, we got three. Nathaniel, Reed, and Maddie. Okay. So the gang's all here. Okay. All right. So, after a jacked up morning already. All right, so let's chit chat about that assignment on that projectile motion. So this stuff is going to be on the final. So I want to make sure everybody's cool with this. So, do you have any ones you specifically want me to work, or you just want me to kind of go through the whole thing?
Maybe just like 8D.
8D? Okay. Well, just let me kind of go through the whole thing.
Okay.
I'll get there. Because it all kind of builds off of each other.
Yeah.
So, on number one, here's the deal. So on number one, even if you look at that question about the baseballs, so here's the setup, here's the baseball, boom, it's going to be launched like this. So this is the deal when you look at what is a factor and what is not a factor in terms of how far this ball is going to fall. So here's the basic idea, is that the longer that ball is in the air, the farther it's going to fall, because the gravity mafia has more time to act on it, okay? So if you look at range equals Vx time, they're both going to travel the same distance. They're both going to go from the pitcher to the catcher. So the range is the same, okay? There you go. So clearly, since they're both going to travel the same distance, the one that has the higher velocity is in the air less time. So therefore, gravity has less time to act on it, and it has less time to pull it down towards the earth. So that's kind of how you want to approach that first question. Is that, okay, don't tell me, oh, the faster ball is going to go further. It's not. They're both going to go the same distance. But it's going to be that relationship between Vx and time. So the faster ball has a bigger Vx. It has less time for gravity to act on it, therefore it won't fall as far, because the distance it's going to fall is 1/2 AT squared. Okay? So based upon this, this isn't like the horizontal distance it travels. This is the vertical distance it's going to fall. So clearly, because that time is squared, so any changes in time, because it's squared, makes a huge difference in terms of how far it's going to fall. So if you really want to get fancy, you would say, oh, because the distance it's going to fall is 1/2 AT squared, the bigger the time, the farther it falls, the more likely it's going to be below the strike zone. Okay, now on number two, so here's the hockey puck, boom, okay? So the first one you want to draw are the forces. So you want to set up a scale, okay, where you're going to go, okay, maybe, because you know the mass is 0.1 kilograms, right? So it weighs 0.98 newtons. So you could come in here and say, okay, hey, maybe I'm going to let 1 centimeter equal a newton, okay? Something simple like that. So therefore, you're only going to draw this thing like 0.98 centimeters long. So you're going to have your gravitational force, your normal force, boom, boom. After it flies off, you've got this. So this is what this first diagram should look like on number two. Show me the scale. Here you go. Now, on the second one, you want to draw the accelerations. Well, and this is this whole idea going into this midterm final, okay? So, to figure out if you're going to accelerate, okay, to see if there's an acceleration, look up here to your forces. If your forces are balanced out, that means that you're not accelerating. Now, if you're not accelerating, one of two things could happen. Either you're at rest, okay, or you're moving with a constant velocity. But that's it. So, look at this. So up here, your forces are balanced. You're just not accelerating. Okay, so there is no acceleration here, and there is no acceleration here. Now, once it flies off, that force, that imbalanced force of 0.98 newtons, if you take that 0.98 newtons, which is your net force, divide that by the mass of 0.1 kilograms, you're going to get an acceleration of negative 9.8 meters per second squared. So you're not accelerating here, but then you begin to accelerate here, because this is why you have an imbalanced force. Okay? So on the test tomorrow, if I say, hey, an object is moving with a constant velocity, there's two situations that could happen. Either the forces are all balanced out, okay, that's an option, right? Even if there was friction, maybe that applied force is balancing out that frictional force, okay, whatever. In this case, I don't have to keep applying a force to keep it moving because it's a frictionless surface. So if you have a constant velocity, either all of the forces add up equal to zero, or if you're in a situation like you're in deep, deep space where there's no gravitational field, then your inertia will just keep you moving at a constant velocity. So there's two ways you can have a constant velocity. Either all the forces add up to equal to zero, or there just aren't any forces, and the inertia will keep it moving at its constant speed. Okay. So, again, show me this scale, like maybe 1 centimeter equals 10 meters per second squared, something like that. So you can have, so this is what that second set of diagrams is going to look like. Nothing, nothing, acceleration, acceleration, imbalanced force, imbalanced force. Okay? Good with that? Okay. Now, your third one is going to be your velocity vectors. Well, it's moving up here, so maybe you're going to let 1 centimeter equal 5 meters per second. Okay? Something like that. So here's the deal. These horizontal velocity vectors aren't changing. And again, here's the big idea. Your horizontal velocity vectors aren't changing because of the fact that you're not accelerating. And you're not accelerating because there's no imbalanced forces. So this is where this whole thing is very sequential. Oh, forces are balanced, we're not accelerating, I'm maintaining the same horizontal velocity. Now, after it falls off, then you have an imbalanced force. Oh, then I just have gravity acting on it without the normal force. Oh, now I got to figure out how fast it's going. So since you don't have time, but you know how far it falls, I'd recommend you use that equation. V squared equals V naught squared plus 2AD. Now, here's what you have to be careful of. What happens in the x stays in the x. What happens in the y stays in the y. So don't set this initial velocity as the 5 meters per second, okay? Because if you're going to use negative 9.8 meters per second squared here, and you're going to use the distance that it's going to fall, don't put in 5 meters per second, okay? It's because mathematically, we're going to treat this thing as if we just drop it. So on a lemming problem, if it comes out horizontal, or if you just drop it, mathematically, the gravity mafia doesn't care. Okay? It's the exact same calculation. So this is going to be important. If I just drop something and let it fall, versus if I shoot it out with an initial velocity of 0, in both situations at the same time, they're both going to fall the same distance. So one of those velocities should be around 3, and the other one should be around 5. Okay, that's an ish, but one should be, that first one should be around 3, the second one should be around 5. Okay. Now let's talk about 5 and 6. So here's what's got to happen on 5. You've got this launch velocity of 32 meters per second, and the angle is what, 30 degrees. So you got to find your Vy, and you got to find your Vx. Now, after you use that velocity, that launch velocity, to find this x and y, these Vx and Vy, never speak of that 32 meters per second again. It is dead to you. okay? Don't use it again, ever, okay? Don't, it's dead. Don't speak of it, okay? Out of these two components, okay, this is what you got to be able to do on the test, because I promise you, you're going to have a question like this on the midterm tomorrow. I promise you, okay? But look at this in terms of a big picture. So I've got an initial velocity of 16 meters per second. So Hannah, I got to find my time up, okay, to reach my maximum height. Since this initial velocity is 16 meters per second, is my time to maximum height going to be bigger or smaller than 1 second?
Bigger.
Why? It is. Why?
Because the height is more than 16 meters.
Nope, that's not why. Think about this. As soon as this thing is launched, this thing is going to begin to slow down vertically, right? So on a vertical, if you were to draw a velocity time graph, you would start here at 16 meters per second and it's going to come down here like this. So since gravity is what's making it slow down, what's the slope of this velocity time graph? Huh?
Acceleration.
Which is?
Gravity.
So this is going to have a slope of negative 9.8 meters per second squared, right? That's what that slope means. So if I started at exactly 9.8, it would take me exactly 1 second to go to 0. So since I'm starting at a number bigger than 9.8 meters per second, I know my time up has to be more than 1 second. Okay, that's it. There you go. So it's always a good idea before you actually start crunching the numbers to step back and go, okay, hey, how is this deal going to play out? Okay, probably be about 1.5 seconds, right? Because if you round up the gravitational acceleration to negative 10, if you started at 10, it would take you 1 second. So I'm at like 1.6, so it's going to take me about 1.6 seconds for this thing to reach its maximum height. Okay, so your time on number 5 should be around 3.3 seconds, okay? Ish, something around 3.3, because that's your total time. So it's going to take about 1.6 seconds to go up. That's going to take another 1.6 seconds to come back down, okay? Now, your maximum height, there's like a whole bunch of different ways you can calculate your maximum height. This is what I would recommend. I'd use that equation, and here's the reason why. Because that's going off of just that initial velocity. I wouldn't use one that has time in it, because if you've screwed up your time calculation, then you're going to screw up this answer, okay? So that's why I wouldn't recommend that you use time. Okay, so you know you're solving for height, so you have v squared minus v naught squared over 2a. It's going to equal d. Okay, there you go. And again, only use that initial vertical velocity. Don't use the 32 meters per second. It's dead to you. Only use that. So what you should see on number 5 is that your height is around 13 and your range is around 90. Okay? Now, the only thing that changes on number 6 is that you're going to swap these two numbers, because now you're going to be at like a 60-degree angle. So your Vx becomes your Vy becomes your Vx. Okay? So on number 6, what you should see, that your total flight time is around 6 seconds, your height is around 40 meters, and that range is still around 90 meters. So what you should see on 5 and 6 is that as you increase the angle, your flight time becomes bigger, your maximum height becomes bigger, but your range is the same. Now, that only works with complementary angles. Like with this one, this is the 30 and 60. If you had 20 and 70, it would do the same thing, okay? 10 and 80, it would be the same thing. Now, if you're comparing like 30 and 80 degrees, the ranges aren't going to be the same, because 30 and 80 aren't complementary angles, okay? So if you have complementary angles, and it only works with complementary angles, The ranges are the same, but the height and time are bigger with that steeper angle. Okay, now, let's talk about number 8. I promise you, I solemnly promise you, that you're going to have a problem like number 8 on the test, okay? It's going to be at the bottom of the front page, okay? Promise you. It's going to involve Sproles. It won't it, Sproles?
Yep.
Yep, okay? Sproles is going to be a key part of that story for your test, okay? So, I like this because it combines a whole bunch of different things. So it's going to come up here like this, right? So at the bottom of the first page of the test, you're going to have a problem like this. There's going to be a problem like this on the review. You work this problem again and again and again and again and again, and then you go, wow, I'm going to change the angle, and then I'm going to work it again, okay? I promise you, this problem is going to be on the test. It's the bottom of the front page. You mark my words, okay? So, what's the first thing that you did with that velocity? Break it up into what? Vx and Vy, right? That's the first thing that you have to do. You got to find Vx and you got to find Vy. Because if that's wrong, everything else is going to be wrong. So your Vx is 20 meters per second and your Vy is 34.6 meters per second. Okay? If that's wrong, everything else is just going to be a train wreck on this problem. So, you want to find the maximum height. What I would recommend is that I'd use v squared minus v naught squared over 2a to find that maximum height. So your answer to 8a measured from the ground is about 80 meters. Because if that's wrong, the rest of this problem is going to go south. Okay? So that's going to be about 80 meters. So on B, you want to find out what's the total flight time. So that total flight time is that you need to find this time up, okay? And again, you're at 34.6 meters per second. So that tells me is if the gravitational acceleration was like -10, that would take about 3.5 seconds to go up. So in just a ballpark, my time up is going to be about 3.5 seconds, okay? That's just going to be my time up. Now, because this is not symmetrical, since I'm like here, but I'm going to fall all the way down to the ground, and it isn't returning back to the same height, I cannot set my time up to be the same as my time down. Okay? I've got to find that time down as separately. Now, what I would do personally, okay, if this were me, I would say, I'm dropping this ball, this is how I would view it. I'm dropping a ball from 80 meters tall, or whatever that maximum height is. Okay, it's about 80. So, when this thing starts its way down, Reha, when it starts its way down, what's its initial velocity? No. What?
0.
0, because it's starting, right, you're at the maximum height. So, on the way down, this thing is starting with an initial vertical velocity of 0. Treat it as like a lemming problem. Oh, I'm up here at 80 meters, I'm just going to drop this thing and let it fall, okay? So, what I would do to get my time down, I'd go distance equals 1/2 at squared plus v naught time. Now, you have to be careful. Again, this is the initial vertical velocity on the way down. And Reha just said that's going to be 0. So I go 2d over a, the square root of that is going to give me my time. This is what I would use to find the time down on a lemming problem or anything that starts from a maximum height and is falling. This is a lovely equation. Embrace it. Okay? Become one with it. It's a great little equation. So anyway, your answer to 8b is about 8 seconds, okay? It's going to be a little bit less than 8 seconds once you combine your time up with your time down. Now, think this through. We said it was going to take about 3.5 seconds for it to go up. So since it has to fall farther, my time down has to be bigger than my time up. Because it started here, it went like this, and then it's going to fall all the way down here like this. So if you find your time down, and it isn't bigger than your time up, you've done something wrong. Okay? So just think through your answers to see if they make any sense. Okay. Then on 8C, you're going to calculate the range, which is going to be Vx time. Okay? Take your horizontal velocity, multiply it by the entire time. So your answer to 8C should be around 150 meters. Okay? Ish. Now, on 8D, is that the one that you...
Yeah.
Yeah. 20 minutes later, we got to the question that you asked. Now, on 8D, when I'm talking about speed, all right, I'm talking about the combined resultant of the x and y velocities, okay? So that's why I tell you, oh, it's the resultant of your x and y velocities. Now, think this through. When this thing was launched, it had an initial vertical velocity of 34.6, okay? So it's going to go up, and then it's going to fall all the way down here. So here's the question. When it lands, is the vertical velocity when it lands going to be bigger or smaller than 34.6? Hannah? Bigger, because it falls further. It doesn't return back to the same point. It falls further. So I know that the vertical component of the velocity has to be bigger than 34.6. Okay, it has to be, because it's going to fall further. So when it lands, it's going to have the same Vx. Okay, so the Vx is still going to be 20 meters per second. Okay? That hasn't changed. That's still 20 meters per second because we're assuming that there are no horizontal forces. But you've got to find the vertical component when it lands. Now, what I would recommend is that you use that equation. On the way down, your initial velocity is 0. You know how far it falls, that 80 meters, right? You know your gravitational acceleration, find your final velocity. Okay? So that final velocity should be around 40 meters per second. Okay? So the final vertical component here is about 40 meters per second, which makes sense because that's bigger than 34.6 that it was launched at. Okay? So at this point, you know two sides of the triangle. You know the horizontal component is 20. You know the vertical component is about 40. You want to find that resultant. So your answer to 8D should be around 45 meters per second.
That's not like
Okay? All right. Well, this is, what'd you get?
74 or something.
Okay, no, bad. What'd you have as your vertical velocity when it landed?
I'm gonna be honest with you, I don't know. I can't read my work right now.
Okay, all right.
I'm just gonna redo it.
Yeah, just redo that one. Yeah, that's a good idea. Yeah, Caden, that's, yeah, just, yeah. Yeah. Now, on E, at the top of the flight, what's the angle between the velocity vector and the acceleration vector? So don't make this difficult. So you're like this, right? So at the top of the flight, what's the only type, at the very top, okay, so you're like this. At the top of the flight, what's the only kind of velocity that it has? X or Y? The very top of the flight. What's the only velocity that it has?
0.
Now vertically it's 0.
Oh.
But it's still going to be traveling with a horizontal velocity of 20 meters per second, right? Okay? So it's still going to have Vx. Well, at the top of the flight, or at any point in the flight, what's the only force acting on it?
Right.
Gravity. And that's going to cause an acceleration pointing straight down. So at the top of the flight, and that's the only time it happens is at the top of the flight, everything else, the acceleration vector and the velocity vector won't be at 90 degrees. But at the top of the flight, that's the only time your velocity vector is going to be at right angles to your acceleration vector. Now, if you just launch it straight up, then your acceleration vector and your velocity vectors will always be parallel to each other if it's launched straight up. So it's only when you have projectile motion at the top of the flight where you can have a 90-degree angle between your acceleration vector and your velocity vector. Okay? Got that? We're cool. We're good. Okay. So, as you prepare for the test, okay, so let's talk some big ideas, all right? So let's say that I've got Hank here, okay? And Hank has a mass of, let's say, 10 kilograms. And then I have Gary the golf ball here. And Gary the golf ball has a mass of 0.1 kilograms, right? Okay, so let's just start at the basics. How much, what is the weight of Hank? So Rayhoff, I said, Hank has a mass of 10 kilograms. I want to figure out how much Hank weighs. What are you going to do? Yep. So I'm just going to take 10 kilograms times 9.8 meters per second squared, and I'm going to get 98 newtons. Okay? So the gravitational attraction between Hank and this Earth that we're on, right? The sum total of all of that, when I let go, is going to be 98 newtons. So that's the force that's going to be acting on Hank. So that's going to be 98 newtons. Now, if you do the same thing with Gary the golf ball, if I take 0.1 times 9.8, that would get me 0.98 newtons. So right away, do not tell me, oh, gravity is the same for everything. It's not, okay? There's much more of a gravitational force on Hank than there is on Gary, okay? Gravity isn't the same. We'll see that it has the same effect, right? But it's certainly not the same. So one of the graphs you all drew back on assignment 4.1 is that you drew a graph of mass and Fg. So here was like 0.1, and that was like 0.98 newtons, and then you're way out here at 10 kilograms, and that's like 98 newtons. And this, you could connect those points, and if you were to find the slope of that line, that would have a slope of 9.8 meters per second squared. So here's one of the key things that you have to understand. That the gravitational attraction on an object is proportional to its mass. The more mass that you have, the more it weighs, okay? So don't tell me everything weighs the same. It doesn't, okay? It's proportional to mass. Now, when I let go of, I'm not going to let go of Hank, by the way, but I'll let go of Gary. So when I let go of Gary, Gary accelerates at 9.8 meters per second squared, okay? Hank is going to accelerate at 9.8 meters per second squared, okay? They're both going to have the exact same acceleration. So the effect of gravity is the same in terms of the acceleration. But here's what's important. Hank has a lot more mass, okay? Hank has a lot more mass. So it's going to take a lot more force to make Hank accelerate at 9.8 meters per second squared than it is to make Gary accelerate at 9.8 meters per second squared, okay? So that's one of the most important things you have to understand, is that the weight of an object is proportional to its mass. The more mass that you have, the more it weighs, but there's more force acting on it, but it also has more inertia, so we end up with the exact same acceleration. Okay? So do not tell me, oh, gravity is the same for everything. It's not. Okay? So, that's going to be one of the key concepts. Make sure that you know, like, your position time graph. So if I gave you a position time graph like this versus a position time graph like this. So, beginnings. What does the slope of a position time graph give you? Velocity. So, this position time graph, right, shows that I'm starting off, I kind of have constant velocity, then I slow down, and then I speed up again, okay? Does this ever show a change in direction?
No.
No, why not? What does it not do? What does the slope not do?
Negative.
Yeah, it never changed the sign, okay? So, this doesn't show a change in direction because your velocity doesn't change sign because your slope never changes sign. If you have a straight sloping line on a position time graph, what does that show you? Constant velocity. So this would be constant velocity because the slope is the same, okay? Now, if you were to have a velocity time graph that looked like this, okay? So here's some positive velocity, right? So, from here to here, am I speeding up or slowing down?
Speeding up.
How do you know? You're right, you are speeding up, but how do you know you're speeding up?
You accelerate the
Your acceleration is,
positive.
and your velocity is,
Positive.
so you're speeding up, okay? Or, here's 0 meters per second. The line is going away from 0 meters per second. That's the other way that you can look at it. Now, here's what you cannot tell me. Do not look at this and go, oh, you're going away from the reference point, okay? You don't know that you're going away from the reference point. The only thing that you know is you have positive velocity. If here's Al, and if Al is the reference point, okay, and this direction is positive, okay, I could be going towards Al with a positive velocity. I could be going away from Al with a positive velocity. But in both situations, I'm still going in a direction. So you cannot tell where you are on a velocity time graph. The only thing that you can figure out is which direction that you're going. So what happens on a horizontal line, Hannah Blair, on a velocity time graph?
It's a constant velocity.
So I'm not accelerating. So at this point, all of my forces add up to equal to 0. So here I have an unbalanced force because I'm speeding up. Here I have a constant velocity, so all my forces add up to equal to 0. Here I'm speeding up again, but I'm not speeding up as much. So on this velocity time graph, if you were to find that area, what would the area on a velocity time graph give you?
Displacement.
Huh?
Displacement.
Displacement, okay? Because you're taking meters per second times seconds. So you got that going for you. Even go back to the beginnings. Look at independent and dependent variables, okay? Force and acceleration, right? So if you look at force and acceleration, which one's your independent variable? Which one's your dependent variable? You know, y'all did the lab where you took the cart, right? And here was the pulley and you hung a weight from the end of it. And I promise you, this concept is going to be on the test. There are problems like this on the review. There were problems like this on the forces test. I promise you. Here's the idea. All you defined this acceleration, the only thing that's going to make this thing accelerate is the weight of what's ever hanging down here. So you have the weight of this divided by the total mass, that's your acceleration. That's all you have to do. And some of you are making this so complicated. Literally, it's this mass times g divided by the total mass. Yes?
Could you explain again on when, because like I know like the different systems, but like, can you explain again when you add the mass of the two objects? Because I'm still not getting that a little bit.
All right, so let's say, I'll draw it a little bit more legibly. Okay? So let's say this is a 1/2 kilogram mass, and let's say that's a 0.1 kilogram mass, okay? And let's just say that there's no friction, all right? So initially, don't even worry about this, okay? Pretend that this isn't even here. Do not even worry about it. The only thing that can make this thing accelerate is if this is being pulled down by gravity, right? So just figure out how much gravity is pulling down on this. Oh, 0.1 times 9.8. Oh, I get 0.98 newtons. So the only thing available to make this thing move is gravity applying a force of 0.98 newtons. That's it. There's nothing else, okay? There's no fans, there's no squirrels, there's nothing, okay? This is the only thing that can make this thing move, right? Now, gravity is pulling down on this one with a force of 4.9 newtons, but there's also a normal force of 4.9 newtons that's balancing it out. So this is why this isn't an opposing force, because the gravity's trying to pull it down, but the table's going, no, we got you, okay? We're not going to let you fall, we got you, okay? This one is screwed, because it's like gravity's pulling down, and there's only the string that's attached to this, so this is like trying to save it, okay? But this is the only force that's available. This is it. There's nothing else. There is nothing else to make this thing move. So that downward force would be 0.98 newtons. So if you look at FAP, opposing, and net, okay? So if there is no friction, and that's the only thing that can impede this thing, is friction, or if it was on an inclined plane, where you would have a force parallel that was acting down. So if this is flat and frictionless, this is it, 0.98 newtons. There is no opposing force, so my net force is 0.98 newtons. There is nothing else. This is it. There is nothing else, okay? Now, to get the acceleration, you divide it by the total mass of the system, which in this case is going to be 0.5 kilograms plus 0.1 kilograms. So the total mass of the system would be 0.6. So I'm going to take 0.98, which is what the gravitational force is, divided by the total mass of 0.6, there's my acceleration. That's it. Boom. There you go. Now, if you change it and you put it like on an incline, like this, okay, then that's a little bit more complicated, because you still have 0.98 newtons trying to drag this thing, right? But now you have this force parallel acting as an opposing force. So then, if you make that positive, you would make that negative. But at the end of the day, so now you're going to have some force parallel acting down. So that means I'm going to shrink my net force, because now I've got to pay off part of the gravity mafia. But at the end of the day, I'm still going to take that smaller net force, and I'm still going to divide it by 0.6 kilograms. I'm still going to divide it by the total mass. Okay, that's it. Now, if you make it where it's an Atwood machine where you have a pulley, and I got 0.5 kilograms over here, and 0.1 kilograms here, so I've got a downward force of 4.9 newtons here, I got 0.98 newtons force here. Now, with this one, the 0.5 here is going to drag the 0.1, because now there's no table balancing it out. All of that gravity is going, oh, here's 4.9 newtons. So again, in this situation, I take 4.9, that's my applied force, subtract that out, because that's my opposing force, and then I would still divide by 0.6 kilograms. I promise you, there's going to be one like this on the test, and I promise you that there's going to be one like this on the test. Okay? Now, here's the deal. Whenever you're dragging something like this, because you're dragging this mass, this acceleration always has to be less than 9.8 meters per second squared. This acceleration cannot be anywhere close to 9.8 because you're dragging this mass with it. Okay? I promise you there's going to be a question like, where you're going to like launch a rocket, okay? Right? And I'm going to give you some applied force, like this, and you're going to have some opposing force, and then you're going to find the net force and the acceleration. Okay? Promise you there's going to be something like that. Promise you. So there's a total of 40 questions on the midterm, okay? It's all multiple choice or true, false, things like that. So what's going to happen tomorrow, it's 2 pages front to back. You're also going to have an answer sheet, and that's where you're going to write the answers for the 40 questions. That's the only thing that I'm going to grade, okay? So for those of you that are watching the studio audience, the only thing that I'm actually going to grade is the answer sheet where you're going to write your answers. So you're going to see 2 columns, 1 through 20, and then 21 through 40. Okay, that's where you're going to put your answers. You don't have to worry about showing your work, keeping it organized. If you want to work on scratch paper, you can. If you want to write on the test, you can write on the test. But the only thing I'm ultimately going to grade is that answer sheet. Now, for those of you that are taking this test at home or something like this, and I know it's all screwed up because of sickness and soccer and anything else. So, if you're taking this test not within this room, at some point I want that physical test back to me, okay? I love you all to death, but I do not want my finals floating around. So at some point, if you're taking this test at home, you can scan it, take a picture of the answer key, or the answer sheet, send that to me, okay? Get that to me right away. But at some point, I want my physical test back, okay? Even if you print it out at home. If I send it to you as a PDF file and you print it out at home, I want that physical test back in my hands as soon as possible, okay? Somehow or another, you get me that test back to me, or I am going to hunt you down. Okay. So, the test, like I said, the test is going to be comprehensive, but it just kind of builds off of each other. Like, you know, the very first day you were in this room, we talked about the units of force. Oh, kilograms, meters per second squared. Guess what? That's what we're still talking about. Okay? So, you have the review. Okay? I also have, for the 3 of you that are here, I've also got a file with all your old tests in them. So if you want to go back and look at your old tests, which is always kind of fun to do, especially if you go back and look at that first test that you took, and you're like, oh my God, how did I miss these questions? Seriously, okay? So you go back and look at those. I'm going to give you the answer key to the review and a blank review. Again, if it were me, this is what I would do. I would not even look at that answer sheet to begin with. I would take that blank review and I would treat that as the final and go, okay, I'm going to work through this thing start to finish. And if you come across problems that you don't know how to do, or if you're sketchy on, you come back later and you work that problem again. Okay? Then you come back later and you work it, but then change the numbers. Oh, hey, I'm going to make a different height. I'm going to make the building taller. Oh, what's that going to do to my time up? What's that going to do to my time down? What's that going to do to any number of things? Okay? Play the what-if game. All right, I am done. So, Zoomers, I want to shut down. You all should have the review. If you don't have it, email me and I will send you a PDF file of that review. But other than that, we're finished. And you all have the rest of the time to either look at old tests, work on that assignment, which I still need, or do the review. So we're done. All right, see you kids.
Are you still doing